Greetings and welcome to the channel for Sleepy Science. We'll be studying lightning tonight, one of nature's most amazing phenomena. Flickering over the heavens from the beginning of time, this phenomenon is both timeless and old. Electrical forces build and release in dazzling light cascades hidden in the accumulating clouds above us. Scientists are still trying to solve the complexities that lie behind what seems to be a simple flash. Lightning is significantly more complicated than it first appears, from the invisible leaders that create channels through the air to the crackling branches that spread over storm clouds. I encourage you to like, subscribe, or leave a brief remark if you appreciate my introspective musings. It also makes it easier for others to find their way here, one drowsy person at a time. For now, however, all you have to do is relax, take a seat, and let the serene magic of lightning lull you to sleep. Let's get started. Characteristics of lightning. Simply put, lightning is the movement of electricity through the atmosphere. Lightning is essentially an electrical discharge. Lightning is the same event on a much larger scale as a little spark that leaps from your finger to a door or knob on a dry winter day. Wanneer waterdruppels en ijskristallen elkaar treffen in stormwolken, worden elektrische ladingen gescheiden. Whereas negative charges build in some areas, positive charges concentrate in others. The air itself can no longer withstand when the divergence gets sufficiently large. In search of equilibrium, a pathway develops as electricity moves from one area to another. We refer to this charge flow as lightning. Even though it seems instantaneous, magical even, it is subject to the same basic physics principles that control even the tiniest spark. Even if the energy is thousands of times more and the scale is different, the basic idea is the same. Nature uses lightning to balance out electrical imbalances in the atmosphere. The majority of lightning strikes inside clouds, out of sight. We frequently envision spectacular bolts striking the earth when we think of lightning. However, the great majority of lightning never makes it to earth. The majority of electrical discharges within a thunderstorm's towering depths take place between various cloud areas. These are referred to as sheet or intra-cloud lightning. The cloud may appear to light up from within from below, flickering and lighting like a lamp behind frosted glass. Because it stays hidden inside the storm, the discharge branches through miles of cloud, taking the easiest routes between ice crystals and water droplets. Because the more spectacular ground strikes often garner more attention, this lightning frequently passes unreported. However, it is much more prevalent. Misschien 3 of 4 bouten blijven volledig binnen de wolken voor elke bout die op aarde komt, stilzwijgend de lading in de storm in balans houden. The type of lightning we are most familiar with is cloud-to-ground. Cloud-to-ground lightning is the type of lightning that most vividly grabs our attention. These bolts strike towers, trees, and open ground as they soar from the base of storm clouds to the surface below. They are created when the negative charges in a cloud's bottom layer get so strong that they try to interact with the positive charges on the surface of the Earth. In reality, what looks like a single bolt is a complicated operation that involves several strokes that quickly follow the same route. The return stroke is the bright flash that we observe, the point at which ground-based energy surges upward to join the channel that is descending. The walkway is so vividly illuminated by this ascending flow. Massive amounts of energy are carried by cloud-to-ground lightning, which heats the air to extremely high temperatures and produces thunder. It is the most recognizable form of lightning, even though it only makes up a small portion of all lightning. The temperature of a lightning bolt is higher than that of the sun. Temperatures in the channel rise to almost 50,000 degrees Fahrenheit during the brief instant when lightning rips through the atmosphere. The sun's surface burns at about 10,000 degrees to put that into context. For a brief while, the pencil-thin lightning channel becomes 5 times hotter than our star. The shock wave that we hear as thunder is produced by the surrounding air expanding explosively due to the intense heat. It's astounding how much energy was released in that split second. However, the heat radiates outward and disappears into the atmosphere practically instantly. Only the thunder remains to indicate the channel's passage as it cools in microseconds. When you see lightning, you see temperatures higher than the sun's surface, focused in a path no thicker than your thumb. The speed of lightning is about 1/3 that of light. Flashes of lightning appear to happen instantly. However, the real speed of the electrical discharge is about 90,000 meters per second, or about 1/3 of the speed of light. This speed is still unfathomable. Lightning might circle the Earth several times in the blink of an eye. Because human vision is unable to discern any delay at such speeds, lightning appears to be instantaneous. It is actually a series of events that we perceive as a single flash. Return strokes rising, leaders descending. Everything happens so fast that it all merges into a single instant. Our eyes perceive the light from the discharge almost instantly, giving the appearance of simultaneity. Even though the electrical discharge is incredibly quick, it still takes a certain amount of time to go from cloud to ground. Collisions within storm clouds initiate the lightning generation process. Soms iets dat lijkt op iets onschuldigs is de voorspanner van een blikseminslag. Numerous ice crystals, water droplets, and soft hail particles known as graupel tumble through strong updrafts and downdrafts inside a growing thunderstorm. These particles swap electrons as they collide and bounce off each other. The larger graupel particles are likely to acquire a negative charge, whereas the smaller ice crystals tend to acquire a positive charge. Miljoenen op miljoenen botsingen veroorzaken dat de storm uiteindelijk elektrisch vormt. Near the cloud's summit, positive charges build up and are transported upward by the lighter, smaller particles. The heavier growl is weighed down by negative charges that sink to the bottom. Binnen de wolken produceert deze scheiding een massieve elektrische veld. Lightning is about to happen. It all started with the basic friction of water and ice falling through the storm. Stepped leads move toward the ground unseen. Iets onzichtbaars wordt gezien die de grondwerkzaamheden voor het schitterende licht legt. A stepped leader, a thin channel of ionized air, starts to descend from the cloud's base. It descends roughly 50 meter tegelijk in snelle flitsen, even stopped voor het verder gaat. Human eyes are unable to perceive this stepwise progression because it occurs too fast and insufficiently. As it falls, the leader forks, forming a network of potential routes to the Earth. Every branch searches the atmosphere for the least resisting route. As this negative charge approaches, it creates a positive charge on the ground below, especially on tall structures like towers, buildings, and trees. Positive streamers start extending upward from these high points to meet the descending charge as the stepped leader gets closer to the surface. Wanneer de gestapelde leider uiteindelijk een omhooggaande streamer raakt, produceert de terugslag de verbluffende flits die we waarnemen. The circuit is finished. Through the ionized conduit, the leader has made a tremendous burst of positive charge shoots upward from the ground in that very moment. The road is vividly illuminated by this return stroke. With tremendous current, it travels upward at almost 1/3 the speed of light. The plasma channel glows white hot as a result of the strong electrical current heating it to temperatures higher than the surface of the sun. We see this flash as lightning. Frequently, what looks to be a single bolt is actually a series of return strokes that rapidly follow the same channel, flickering so fast that they appear continuous. Every stroke that comes after it follows the route that the first one cut out, giving the impression that the flash is flickering or stuttering. Less than a second passes between the leader and the return stroke. It is possible for lightning to repeatedly strike the same spot. There is proof that the adage, "lightning never strikes the same place twice," is untrue. Dozens of strikes occur annually on tall buildings, such as New York's Empire State Building. Once lightning has discovered a good path to the ground, it stays appealing for more strikes. Because they extend closer to the cloud base and offer stronger grounding than their surroundings, skyscrapers, towers, and lone trees on hilltops are struck repeatedly. Future lightning strikes are not deterred by the existence of an earlier hit. As the electrical field recovers between discharges, a single storm may actually hit the same spot more than once. Given how infrequent lightning strikes were at any particular location, the belief most likely developed. However, there is no scientific or statistical barrier to multiple strikes. Lightning doesn't follow superstition. It follows physics. Furthermore, favorable pathways will be employed repeatedly due to physics. Though lightning is dazzling, its pathways are extremely limited. The actual electrical channel of a lightning bolt is surprisingly narrow, usually only around 1 inch in diameter, despite the bolt's huge and monstrous appearance in images. It is the superheated air surrounding this tight core that gives us the bright glow we observe. The bolt appears significantly broader than it is due to the bright light radiating outward. This is comparable to how a far-off streetlight manifests as a big, luminous sphere. The bulb itself is actually fairly modest. Temperatures become so severe because of the narrowness of the channel, which concentrates electrical energy into a very small area. Wider lightning paths would result in lower temperatures and more evenly distributed energy. By directing tremendous force through channels no thicker than a pencil, nature has elegantly solved the problem. Thunder is a sound that is produced when air explodes. Air expands aggressively and quickly as lightning heats the air channel to extremely high temperatures. A shock wave is produced by this explosive expansion, and it spreads in all directions. Thunder is this shock wave. The wave travels faster than sound at first, but it soon decays into a regular sound wave that moves at about 760 miles per hour. Since the lightning channel frequently stretches for kilometers, and the sound comes from every place along that channel, the crack or boom we hear is this wave hitting our ears. As the sound from various parts of the bolt reaches at slightly different times, thunder rumbles and rolls simultaneously. Nearby thunder can be a loud, even painful crack, while distant thunder sounds like a long, rumbling rumble. The sound conveys details about the path and distance of the lightning. Doortelling seconden kun je de afstand van een blikseminslag bepalen. Lightning is visible almost instantly because light moves so fast. However, sound moves far more slowly. You can determine how far away the lightning strike was by timing the number of seconds that passed between the lightning flash and the thunder's arrival. The speed of sound is approximately 1 kilometer every 3 seconds or 1 mile every 5 seconds. The strike was around a mile away if you count to 5 between lightning and thunder. Although this method gives a decent estimate, it is not entirely accurate because topography, temperature, and wind can all alter sound. The interval between the flash and our thunder shortens as the storm gets closer. The lightning are dangerously close when they almost happen at the same time. For eons, people have employed this straightforward counting technique, a method to determine your level of risk and the storm's vicinity. You can't hear thunder more than 10 miles away. Before thunder entirely evaporates, it can only go so far. The Earth's curvature and atmospheric circumstances restrict the sound's range, despite the fact that it is powerful where it originates. Thunder becomes inaudible to humans beyond a distance of about 10 to 12 miles. This implies that distant lightning can illuminate clouds without making any noise as it flashes softly on the horizon. Although it is just regular lightning that is too far away for its thunder to reach you, this type of lightning is frequently referred to as heat lightning. It can be both lovely and unsettling to hear the quiet of distant lightning. Great stille flitsen bloeiden over de lucht, like seeing through a soundproof window at a storm. It serves as a reminder that a lot of atmospheric activity goes unnoticed, stil maar zichtbaar. Windows and buildings can be rattled by close lightning. Thunder that accompanies a nearby lightning strike is not only loud, but also physically strong. The shock wave may be powerful enough to trigger automobile alarms, shake walls and rattle windows. Soms, mensen die dicht bij een close strike staan, zeggen dat ze de percussie in hun borst voelen. Een klop, vergelijkbaar met te dicht bij een luidspreker staan. Het kan schokkend, zelfs eng, zijn om het plotselinge harde geluid gevolgd door een felle lichtflits te horen. Wanneer je dicht genoeg bent om de kracht van de storm zelf te ervaren, is het op zijn intenste. Unmistakable and unforgettable is the piercing crack of neighboring thunder. It acts as a powerful reminder of how much energy goes into every discharge. Thankfully, the majority of people witness lightning from a safer distance, where the thunder is powerful but not debilitating. Lightning types. Though uncommon, positive lightning is incredibly potent. Soms ontstaat een blikseminslag vanuit het positief geladen gebied aan de top van de stormwolk. Maar de meeste blikseminslagen brengen negatieve lading van wolk naar aarde. Though they make up less than 5% of total cloud-to-ground lightning, these positive lightning strikes are far less frequent but far more potent. Positive strikes frequently happen near the fringes of a storm system or as a storm is dispersing. They can strike under a clear sky, giving rise to the expression, a bolt from the blue. Positive lightning is more damaging than negative lightning because it carries a considerably higher current and lasts longer. They can fly horizontally for several miles before falling to the ground. Many of the most serious lightning damage reports, particularly those involving flames and structural damage, are caused by it. A disproportionate amount of lightning-related incidents are caused by positive lightning, despite its rarity. In ribbon lightning, several parallel streaks are produced. Occasioneel, zoals de vele stakingen plaatsvinden, windscheert de bliksemkanaal horizontaal. Several parallel lightning bolts appear side by side because each return stroke rapidly follows the same course, while the wind slightly changes the channel in between strokes. We refer to this as ribbon lightning. It appears to onlookers on the ground that several bolts have struck in parallel lines at the same time. As if reality had briefly shown multiple representations of the same bolt, the effect is startling and a little confusing. Ribbon lightning is quite uncommon and necessitates particular wind conditions at the altitude at which it occurs. Wanneer het verschijnt, produceert het een uniek patroon dat het onderscheidt van reguliere bliksem. An illustration of the intricate relationship between environment and electricity. Branches of forked lightning in the sky. The forked bolt, when the main channel divides into several branches as it falls, is arguably the most recognizable image of lightning. As it descends, the stepped leader explores several routes in search of the least difficult one, which leads to this branching. While some of these branches end in mid-air, others reach the ground. The distinctive tree-like structure is visible when the entire network is illuminated by the return stroke. As the discharge evolved, each branch symbolized a potential route that was investigated. The chaotic exploratory nature of electrical breakdown in air is exemplified by forked lightning. No two lightning bolts with forks are alike. Each is influenced by the particular atmospheric circumstances at the time. The way moisture is distributed, whether dust and ice are present, and a host of other variables. Nature's fingerprint is the end result. Sheet lightning illuminates entire clouds from within, a unique and unrepeatable phenomenon. We only perceive a diffuse glow instead of discrete bolts when lightning strikes deep within a cloud, or when the bolt is hidden by other clouds. We refer to this as sheet lightning. From a distance, the entire cloud, or a significant section of it, appears to briefly light up, flickering with interior illumination. Like a far-off lamp turning on and off, this can be lovely and soothing. Sheet lightning is more prevalent in distant storms or in the last phases of a thunderstorm. The lightning is not any less powerful because there are no bolts visible. It is simply obscured from direct observation. Hours of sheet lightning can produce soft light pulses that decorate the night sky. Een rustige, bijna hypnotiserende prestatie. Segments of bead lightning are luminous. Soms breekt een bliksemstraal in lichte stukken uiteen als hij vervaagt, waardoor een rij heldere kralen langs de kanaal loopt. This short-lived, poorly understood phenomenon is known as bead lightning or chain lightning. It could be caused by anomalies in the lightning channel's cooling or by our perception of the light's uneven deterioration along the journey. Witnesses say it looked like a string of pearls that was momentarily suspended in mid-air. Bead lightning is hard to capture on camera and is still a little enigmatic because it is so erratic and transient. It serves as a reminder that despite our current understanding, lightning still shocks us and presents variations that are difficult to interpret. Ball lightning is still a mystery to science. Ball lightning is arguably the most mysterious type of lightning. Luminous balls of light that are said to float across the atmosphere when thunderstorms occur. Witnesses report seeing balls of light that range in size from a golf ball to several feet, hover or float horizontally, occasionally pass through windows or walls, and last anywhere from a few seconds to a minute before disappearing. Ball lightning has been reported several times throughout history, although nothing is known about it. It is uncommon, erratic and challenging to research. Some onderzoekers hebben plasma-gebaseerde hypothese voorgesteld. Although no single explanation has been confirmed beyond a reasonable doubt, some propose chemical processes or visual illusions. The phenomenon is persistent enough to garner attention, but obscure enough to defy explanation, hovering on the brink of scientific knowledge. It is the biggest unsolved riddle of lightning. The energy and strength of lightning. Er is een enorme hoeveelheid energie in een enkele bliksemstraal. In a normal lightning flash, the strength is hard to understand. Up to 200,000 amps of current and more than 100 million volts of voltage can be carried by a single bolt. Power levels can reach several gigawatt-hour tijdens de korte ontleding. But this tremendous power is only present for a few microseconds. In actuality, a typical lightning bolt's total energy is quite low by industrial standards, roughly equal to 200 kilowatt-hours of electricity, or the energy contained in 1/4 ton of coal. The delivery of the energy, not the total amount, is the issue with using lightning. Any realistic capture system cannot handle the speed and violence of all that power which arrives in a millionth of a second. For practical purposes, lightning's energy would need to be stored instantaneously and then released gradually, a technological hurdle that has proven challenging to solve. About 100 blikseminslagen vallen per seconde op aarde. Approximately 2000 onweersbuien zijn wereldwijd actief op elk moment. Samen produceren deze stormen bliksem op een schrikbarende snelheid. Approximately 100 lightning strikes occur on Earth per second, or approximately 8 million times a day, according to scientists' estimates. As long as there has been a thunderstorm-producing environment on Earth, there has been a steady stream of electrical discharges. De verdeling van de frequentie is niet uniform. Naturally, lightning strikes far more frequently in tropical regions than in Arctic ones. and some places are hit much more frequently than others. However, lightning is an almost constant occurrence on average around the Earth. As you safely relax here, a never-ending light show is playing throughout the atmosphere, with lightning flashing repeatedly someplace. De frequentie van stakingen varieert sterk per regio. Lightning does not strike at random anywhere in the world. Because of their topography and environment, some areas are hit remarkably frequently. Lightning strikes more frequently in Central Africa than any other region of the world, especially in the Democratic Republic of the Congo. Another hot place in Venezuela is Lake Maracaibo, where mountain breezes and warm lake water produce thunderstorms almost every night. Florida, particularly the area between Tampa and Orlando, is referred to as the lightning capital of the United States. These areas are similar in that they are hot and humid and have a topography that promotes storm formation. In contrast, lightning rarely occurs in polar regions, and in some deserts, it may be years before a strike occurs. Due to the unequal distribution, lightning strikes almost every day for some people and infrequently for others. Human mythology and history have been influenced by lightning. Lightning has evoked wonder, fear, and adoration throughout human history. Ancient societies believed that lightning was a gift from the gods. Zeus, according to the Greeks, threw thunderbolts from Mount Olympus. Thor's hammer, Mjolnir, was credited by the Norse. Jupiter was revered by the Romans as the thunder deity. From the lightning serpents of Australian Aboriginal mythology to the thunderbird of Native American folklore, indigenous societies all across the world have created their own interpretations. Lightning was interpreted as a sign of heavenly favor or disapproval and as a weapon of the gods. It may kill trees, start fires, and hit individuals as if at random. Lightning was viewed as otherworldly in the absence of scientific understanding. These tales became ingrained in literature, art, and religion, impacted behaviors, and molded communities. Lightning has just moved from the divine to the understood in the last few centuries. Lightning was shown to be electricity by Benjamin Franklin. In the 18th century, nothing was known about lightning. There were many who thought it was essentially distinct from the static electricity that could be produced in scientific settings. During a thunderstorm in 1752, Benjamin Franklin carried out his well-known kite experiment. He proved that lightning was, in fact, electricity by using a kite with a metal key attached to extract electrical energy from the storm clouds. This marked a turning point in scientific history by turning lightning from an enigmatic force into a phenomenon that could be investigated and comprehended. Franklin's efforts directly contributed to the development of the lightning rod, a straightforward tool that could shield structures by giving lightning a secure route to the earth. His experiment was risky. Despite the deaths of others who tried similar trials, it radically altered how people interacted with storms. Buildings are protected by lightning rods, which offer a route to the earth. One of the simplest and most efficient lightning protection tools is the lightning rod, which Benjamin Franklin created in the 1750s. Simply said, a lightning rod is a pointed metal rod that is positioned at the top of a building and is connected to a grounding system that is buried in the ground by a thick conductor. Bypassing the structure itself, the rod offers a low-resistance conduit for the electrical current to safely go into the ground during a lightning strike. Lightning rods do not draw lightning from farther away, unlike what many people think. Rather, they make sure that the energy is safely diverted away in the event that lightning strikes the building. Numerous structures have been spared from structural damage and fire thanks to properly built lightning protection systems. The idea is sophisticated. Let lightning have what it wants. a way to ground it and stop it from figuring out a damaging way to get through the structure on its own. Natural lightning. Wildfires naturally start when lightning strikes. Although lightning is frequently perceived as harmful, it has been a part of ecosystems for millions of years. One of the main natural causes of wildfires, especially in woods and grasslands, is lightning strikes. Dry wood can be rapidly ignited by the extreme heat produced when a bolt strikes a tree. These lightning-caused fires are actually advantageous in fire-adapted ecosystems, such as some pine woods and prairies. They make room for new growth, remove dead vegetation, and replenish the soil with nutrients. Fire is necessary for the germination of seeds in many plant species. Before people tried to put out every fire, lightning-caused burns frequently shaped landscapes and preserved biological equilibrium. Fire and lightning have a long history together, a cycle of nature that has molded grasslands and forests over millions of years. Soil is fertilized by nitrogen molecules produced by lightning. Beyond its immediate dramatic effect, lightning has another positive impact. Nitrogen molecules in the air are broken apart by the intense heat of a lightning bolt. The nitrogen oxides that are created when these nitrogen atoms mix with oxygen dissolve in rain and fall to the ground as nitrates. These nitrates are a type of organic fertilizer that is necessary for the growth of plants. Scientists estimate that lightning generates millions of tons of nitrogen compounds annually worldwide, making it one of the main sources of fixed nitrogen in the environment prior to the development of synthetic fertilizers. Ecosystems have benefited from this natural fertilization throughout Earth's history. Therefore, each thunderstorm contributes to the soil's fertility in addition to being a spectacular spectacle. The Earth is fed by lightning in ways that are not visible to the naked eye. In sand, lightning can form glass sculptures. Amazing things can happen when lightning strikes a beach or sandy soil. The sand is instantly melted by the intense heat, which reaches temperatures of about 50,000 degrees. The molten material solidifies into fulgurite, a hollow, root-like structure of natural glass, as the lightning channel forms a branching pathway through the sand. These formations can follow the direction of the electrical discharge for several feet underground. Although fulgurites are delicate and frequently fragment during excavation, collectors value whole specimens. They are tangible, glass-frozen records of lightning strikes. Because of the electrical path and the sound's composition, each one is different. Holding a fulgurite is like holding a flash of lightning power that nature itself has turned into a delicate, everlasting art. Although lightning strikes are uncommon, they can be fatal to people. Even though lightning strikes occur frequently around the world, it is statistically uncommon for any one person to get struck. For instance, the odds of getting struck in a particular year are about 1 in 500,000 in the United States. Lightning is still one of the leading weather-related causes of fatalities and serious injuries, nevertheless. In the United States, lightning kills between 20 and 30 people a year and injures many more. During storms, victims are frequently stranded outside, standing in open fields or seeking cover behind trees. A lightning strike's electricity can cause severe burns or stop the heart. Even survivors frequently sustain long-term brain damage. Precautions are necessary since the danger is so real. However, most people will never have a close call because of its rarity. Although lightning is harmful, it can be avoided with awareness and consideration. Some humans are able to withstand several lightning hits. However, the majority of individuals never come into contact with lightning. Some unfortunate people have been hit more than once. The most well-known is Roy Sullivan. a park ranger in the United States who survived 7 lightning strikes between 1942 and 1977, albeit with some damage. He was inducted into the record books for his improbable record. Throughout his career, each strike took place in a different setting and under a different set of circumstances. It is statistically uncommon to be struck once. It seems nearly impossible to be hit 7 times. But that did happen. Although lightning obeys the laws of physics, Sullivan's experience serves as a reminder that exceptional things can happen by coincidence. His ability to survive all 7 strikes is a result of both good fortune and medical attention. Jets, elves, and sprites are unusual lightning occurrences that flash over storms. Strange lights above thunderstorms were sporadically observed by pilots for ages, but these reports were frequently disregarded. Scientists have only verified the occurrence of fleeting bright flashes in the upper atmosphere in the last few decades, thanks to the development of high-speed cameras. Reddish flashes, known as sprites, are seen above massive thunderstorms that extend upward from the cloud tops towards space. Although they are imperceptible to the untrained eye and last barely milliseconds, they can be caught on video. Even higher in the atmosphere, elves are growing circles of light. Thunderclouds are topped with blue jets that shoot upward. The electromagnetic pulse from powerful lightning discharges below, which momentarily ionizes the thin upper atmosphere, is what causes these events. Their beauty, ethereality, and transiency demonstrate how lightning's impact goes well beyond storms. Eruptive plumes are where volcanic lightning forms. A typical thunderstorm is not necessary for lightning to form. Lightning can crackle through the ash plume emerging from the crater during violent volcanic eruptions. The same charge separation mechanism that produces thunderstorms also produces volcanic lightning, but instead of ice and water colliding, ash and rock pieces scrape against one another to produce static charges. The outcome is amazing. The plume of volcanic ash was dark and roiling, with flashes of lightning. Photographs of lightning and volcanic eruptions are some of the most stunning images of nature because they capture 2 of the most potent natural events together. Ancient peoples probably saw volcanic lightning, which could have strengthened myths that associated lightning with divine wrath. It serves as a reminder that electrical discharge lies at the heart of lightning and that numerous processes can produce the required circumstances. Scientists can better understand storms by using rocket-triggered lightning. Scientists occasionally send tiny rockets with long wires into thunderstorms to see lightning in controlled settings. Lightning that would not have otherwise happened at that precise moment is caused by the wire, which creates a conductive conduit from cloud to ground. Using instruments placed along the lightning's path, this technique enables researchers to examine the characteristics of lightning. Numerous details regarding the internal structure of lightning channels, the rate of discharge, and the energy involved have been made public by rocket-triggered lightning. Despite the hazards and need for exact timing, it has emerged as a useful tool in lightning study. These man-made lightning strikes follow the same physics and behave just like real lightning. They just happen whenever and wherever scientists choose, turning an erratic, chaotic event into a repeatable experiment. Lightning strikes Catatumbo almost every night. A spectacular event takes place near the Catatumbo River's mouth in Venezuela, where it empties into Lake Maracaibo. Thunderstorms form almost every night, with hours of non-stop flashing lightning. This is the most regular lightning show on Earth, happening up to 260 nights a year. The convergence of winds from the Andes, the Caribbean, and the lake itself creates ideal circumstances for thunderstorm production, which is what causes the storms. The area is currently referred to as the world's lightning capital. The nearly nightly displays, which may yield up to 40,000 lightning flashes in a single night, have become familiar to the local population. Historically, sailors navigated by the glow on the horizon, using the continuous flashes as a natural lighthouse. It has even been suggested that the phenomenon might qualify as a UNESCO World Heritage Site. Similar concepts apply to lightning on other worlds. There are more planets having lightning besides Earth. Lightning has been seen on Jupiter, Saturn, Venus, and perhaps Uranus and Neptune by NASA spacecraft. The fundamental process is still the same: electrical discharge after charge separation in an environment. But the specifics are different. Lightning can arise in sulfuric acid clouds on Venus. Storms in the huge, turbulent atmospheres of Jupiter and Saturn produce lightning that is far more potent than anything found on Earth. The gases at play are distinct. The idea is the same, but mostly hydrogen and helium instead of nitrogen and oxygen. Lightning is not specific to our planet. It is a common atmospheric phenomenon. Scientists can learn more about other worlds' atmospheres and weather systems by detecting lightning there. It serves as a reminder that electrical storms are woven throughout the solar system's planetary atmospheres. Technology and lightning. Lightning has the ability to interfere with electrical and electronic systems. Lightning is a serious threat to the electrical and technological networks that are essential to modern society. Massive surges that damage transformers and other equipment can be sent through the electrical grid by a direct strike to a power line. Through electromagnetic induction, even nearby lightning strikes can cause currents to flow through metal conductors. These surges have the potential to harm sensitive devices, including computers, televisions, and communication systems. For this reason, surge protectors are advised for expensive equipment. Power companies spend a lot of money protecting transmission lines and substations against lightning. Lightning continues to be a major contributor to power disruptions during storms in spite of these efforts. One strategically placed strike has the power to completely darken entire cities. A persistent problem that calls for continuous technical solutions is the interaction between lightning and our modern infrastructure. Frequently, aircraft are hit without suffering significant harm. Unbelievably frequently, lightning strikes commercial aircraft, approximately once a year on average for each aircraft. Although this may sound concerning, contemporary aircraft are built to safely manage it. Because the metal skin of the airplane serves as a Faraday cage, electrical current can circulate around the outside of the aircraft without entering the interior, which houses the electronics and passengers. Static discharge wicks are tiny devices affixed to the tips of wings and the surfaces of the tail that allow the energy to escape. Flights usually proceed as usual after a lightning strike, although the aircraft is assessed for damage. Pilots report hearing a loud blast and witnessing a flash, but the systems continue to function. Decades of engineering and testing have produced this sturdy architecture. Aircraft lightning strikes are frequent, anticipated, and taken into consideration by aviation safety procedures. Real-time storm tracking is provided via lightning detection networks. Advanced lightning detection networks used in modern meteorology are remarkably accurate at pinpointing individual lightning strikes. Ground-based sensors triangulate the site, frequently to within a few hundred meters, by detecting the electromagnetic pulses generated by each discharge. The public, emergency management, and weather services receive this data in real time. Forecasters can trace the course of storms and determine where they are most intense by using lightning detection. It helps utilities foresee power system issues and provide alerts for outdoor activities. In addition to ground networks, satellite-based detectors offer coverage across oceans that are inaccessible to terrestrial sensors. When combined, These systems produce a complete picture of lightning activity around the globe, turning previously unpredictable and invisible data into plotted, tracked information that prevents fatalities and safeguards property. Lightning is studied by scientists to enhance safety and predictions. Scientists are still working to better understand lightning. High-speed cameras are used by scientists to record lightning in incredibly detailed images, allowing them to see the discharge process step by step. During storms, they use specialized equipment to measure electromagnetic radiation, current flow, and electrical fields. By simulating the generation of lightning and thunderstorms, computer models aid researchers in comprehending the intricate physics involved. There are real-world uses for this research. Gaining more knowledge helps forecasters anticipate when and where lightning is most likely to occur. It influences safety regulations and building codes. It directs the design of communication networks, power systems, and airplanes. New findings improve our understanding every year. Our predecessors thought lightning was completely enigmatic, but with careful measurement and diligent study, more of its secrets became clear. Safety precautions against lightning can save lives. Tragedy can be avoided by being aware of how to act during thunderstorms. During a storm, a hard-topped metal car or a large building is the safest place to be. Steer clear of vast fields, hilltops, and tall, isolated things like trees if you're caught outside. As the lightning current radiates outward from the strike point, avoid lying flat on the ground. To reduce touch with the ground, kneel low with your feet together instead. Water is especially hazardous. When thunder is heard, get out of lakes, beaches, and swimming pools right away. The 3030 rule offers direction. Wait 30 minutes after the previous thunder before going back outside, and seek cover if there are less than 30 seconds between lightning and thunder. Lightning casualties have dramatically decreased as a result of these straightforward guidelines that are frequently taught and promoted. The best defenses are observance of safety regulations and respect for the storm. Lightning's beauty. Clouds are ethereally beautiful when illuminated from within by lightning. The power of lightning to illuminate entire cloud formations is one of its most captivating forms. Lightning inside clouds produces an amazing show during evening storms, when daylight has dimmed but darkness has not yet fully set in. The structure of the storm is revealed by each flash, displaying the layered complexity of the storm system, the curved edges of anvil clouds, and tall cumulus forms. Soft, nearly brilliant glows are produced as the light diffuses over ice crystals and water droplets. Depending on the atmosphere, colors change from white to pale blue, occasionally with traces of pink or purple. This soft light is mesmerizing, like the sluggish respiration of some enormous monster. Wave after wave of light pulsed through the clouds. One of nature's most serene yet potent spectacles is to watch sheet lightning dance across the horizon. Photographers use beautiful long exposures to photograph lightning, with devoted fans tracking storms to get the ideal shot. Lightning photography has evolved into an art form. Cameras can capture the fine branching structure of lightning bolts in stunning detail thanks to long exposure techniques. It is possible to capture multiple hits in a single frame, producing incredibly intricate visuals. In order to maintain camera stability during exposures that take seconds or even minutes, photographers use tripods to place themselves miles away from active storms. Frequently, the outcomes are astounding. Lightning bolts that are frozen against a gloomy sky, illuminating scenery, reflecting off water, or casting shadows on trees and buildings. Rare occurrences like sprites or ball lightning are photographed by certain people. In addition to demonstrating the might of nature, these photographs have scientific value. since they provide information on the structure and behavior of lightning that could otherwise be overlooked. Images of ethereal beauty are produced when art and science are combined. Reflections from lightning on water are like mirrors. The visual effect is doubled when lightning strikes over bodies of water. The bolt itself produces a symmetrical image of light as it bursts from cloud to surface, and its flawless reflection emerges in the water below. Photographers cherish these moments, using the calm or softly rippling water as a natural mirror to capture lightning over lakes, rivers, and oceans. The lightning appears visually longer and more dramatic due to the reflection. These scenes are especially spectacular at night. Both the lightning and the lighted clouds above are reflected by the inky lake. Cities close to bodies of water, like those by huge lakes or the coast, may have breathtaking displays when reflections, urban lights, and lightning mix to create intricately layered visuals. Even though these moments are brief, just a few seconds, they have a profound impact on those who are lucky enough to see them. The dancing patterns of lightning can be seen in time-lapse videos. Time-lapse photography captures lightning as a continuous dance rather than discrete flashes during thunderstorms. By compressing hours of storm activity into minutes of video, the method reveals patterns that are not obvious in real time. It seems as though lightning pulses rhythmically, flashing in nearly orchestrated sequences. Frequent strike areas emerge, indicating the concentration of the storm's electrical energy. As lightning flickers throughout, the storm's actual path becomes apparent, with clouds forming, shifting, and dispersing at a rapid pace. In a complicated electrical ballet, these movies frequently show several forms of lightning: cloud to ground, intra-cloud, and even the uncommon sprites above the storm, all happening at the same time. Online, time-lapse videos of storms have gained popularity, enabling millions of people to enjoy the splendor and strength of lightning from the comfort and safety of their own homes. Festivals of lightning honor the electrical displays found in nature. Communities in areas where lightning strikes frequently have celebrated the occurrence with festivals and get-togethers. Tourists travel to Lake Maracaibo in Venezuela expressly to see the Catumbó lightning, where they stay in local lodgings and take in the nightly spectacles. Storm chasers congregate during tornado season in some locations of the United States. Although their main attraction is tornadoes, supercell thunderstorms accompanying lightning offers amazing bonus shows. Instead of instilling dread, these occasions promote a culture of gratitude. In addition to enjoying lightning's visual features, people learn about its science and safety. What might otherwise be a cause of worry is transformed into a cherished natural wonder through photography classes, informative lectures, and group viewing events. These assemblies acknowledge that lightning is beautiful and deserving of awe, even though it is strong and needs respect. Lightning in history and culture. Lightning was considered a divine power by ancient peoples. We must keep in mind that our predecessors had no idea what electricity was in order to comprehend how they perceived lightning. Lightning was uncontrollable, struck with destructive force, and appeared out of nowhere. Not surprisingly, they ascribed it to the gods. Lightning was a part of almost every ancient culture's mythology. It stood for supreme authority, divine judgment, or the major deity's sword. On lightning-stricken places, which were regarded as holy ground touched by the divine, temples were occasionally erected. Priests and shamans claimed to be able to decipher the messages of lightning, interpreting omens in the location and pattern of strikes. The idea that lightning was a direct message from the supernatural influenced religious rituals, war and peace decisions, and the organization of communities. This idea didn't start to change until the Enlightenment and the advent of science. Symbols of lightning can be seen in many cultures. The lightning bolt picture has evolved into a potent emblem that transcends its natural origins. Zeus and Jupiter were associated with thunderbolts in ancient Greece and Rome, which stood for absolute power. Lightning was frequently associated with thunder figures or spirits in Native American art and spiritual rituals. Thor's lightning served as both a weapon and a means of blessing people in Norse mythology. This symbolism has been maintained in modern usage. Lightning bolts represent strength, speed, and quick action. They can be found on superhero costumes, corporate logos, sports team badges, and military insignia. The sign, which conveys ideas of strength and vitality, is instantly identifiable. Lightning's enduring influence on human consciousness is demonstrated by its continuation from ancient religious significance to contemporary secular use. The sign has evolved into an archetype that stands for both metaphorical and natural energies. Lightning rods decreased flames and altered architecture. Prior to lightning rods, one of the biggest threats to buildings, particularly large ones with steeples and towers, was fire. Devastating fires are often caused by lightning strikes that ignite wooden roofs and frames. Being among the highest structures in the majority of communities, churches were especially at risk. When houses of worship burnt, onlookers did not fail to notice the irony. The lightning rod, created by Benjamin Franklin, transformed urban planning and design. Simple metal rods attached to the ground could now be used to safeguard buildings. For protected buildings, insurance firms started to offer reduced premiums. As the likelihood of lightning-caused fires decreased, cities grew safer. One of science's greatest practical achievements is the widespread use of lightning protection, a straightforward idea that has been methodically used to save innumerable structures and lives. Additionally, it signaled a change from passive acceptance to active protection in the human connection with nature. Early electrical experiments were motivated by lightning. Early scientists did not immediately see the link between lightning and electricity at the laboratory size. The amazing force of lightning seems fundamentally different from static electricity produced by rubbing glass or amber. Systematic electrical investigation was made possible by Franklin's proof that they were the same phenomenon. Scientists discovered that the same rules that applied to tiny sparks also applied to large-scale discharges. This realization sped up research on electricity in the late 18th and early 19th centuries. Building on this basis, scientists like Michael Faraday, Alessandro Volta, and Luigi Galvani gradually solved the puzzles of electrical current, voltage, and magnetism. Humanity's first experience with high-voltage electricity was, in a way, lightning. In order to comprehend it, ideas and mathematical formulas that would eventually facilitate the electrical revolution that drives contemporary society had to be developed. In myth and fiction, lightning has been used as a weapon. Throughout history, people have been captivated by the notion of manipulating or using lightning as a weapon. Thunderbolts were weapons used by mythological gods to defeat adversaries and establish their power. In contemporary fiction, this topic persists. Lightning is controlled by heroes and villains who use it as a symbol and a means of control. Technology has been used in science fiction to control lightning and produce comparable effects. Although it is still unfeasible to really use natural lightning as a weapon, the idea endures in popular culture. Electrical discharge devices and directed energy weapons are examples of attempts to control lightning-like power. The desire to dominate nature and reverence for lightning's strength are both reflected in the idea of controlling such an elemental force. Lightning continues to be the quintessential symbol of unadulterated, nearly uncontrollable energy in both contemporary and ancient mythologies. The strongest lightning is produced during lightning-generating supercells and thunderstorms. Thunderstorms are not all the same. The most potent kind are supercell thunderstorms, which are distinguished by revolving updrafts known as mesocyclones. These storms can create severe weather, such as tornadoes, damaging winds, huge hail, and a lot of lightning, and they can linger for hours. Supercells' powerful updrafts create the perfect environment for charge separation by bringing ice and moisture particles high into the atmosphere. Multiple lightning strikes per second can occur in supercells, making lightning almost constant. Complex electrical fields produced by the storm's revolving structure produce a wide range of severe lightning activity. Supercells are sought after by storm chasers for their amazing lightning displays as well as their potential for tornadoes. The most potent electrical generators found in nature are these storms, enormous energy-producing machines that rule the sky and the terrain. Tempests are fueled by warm, humid air. Certain atmospheric conditions are necessary for the formation of thunderstorms. The main component is wet, warm air close to the surface. This air gets buoyant and starts to ascend when the ground warms from the sun. Under ideal circumstances, it keeps rising and cools as it does so. Further upward motion is fueled by the latent heat released as the moisture condenses into water droplets. Towering cumulonimbus clouds are formed by strong updrafts generated by this positive feedback. Lightning is caused by electrical charges created by ice and water particles colliding within these clouds. Thunderstorms cannot form if there is not enough moisture and warmth. For this reason, lightning occurs less frequently in cold, arid climates and more frequently in tropical and subtropical areas with plenty of warmth and humidity. Forecasters can more accurately estimate when and where storms will form when they are aware of these requirements. Where lightning strikes is influenced by mountain ranges. The dispersion of lightning is significantly influenced by topography. Air is forced upward by mountain ranges, cooling it and causing precipitation and cloud formation. Thunderstorm conditions are favored by this orographic uplift. The prevailing winds that face the terrain force hot valley air upward, causing afternoon thunderstorms to occur often in areas directly downwind of mountains. Throughout the summer, the Rocky Mountains in the western United States frequently produce thunderstorm activity. Local lighting patterns are also influenced by the Andes, Alps, and Himalayas. The location of storms can be influenced by even tiny hills and ridges. When forecasting lightning risk, meteorologists take geography into consideration. High peaks themselves are commonly struck because of their exposure and elevation, and lightning strikes are more common in mountainous areas than in nearby lowlands. It is possible to map and predict the patterns that are produced by the interaction of atmosphere and topography. Lines of severe storms are triggered by frontal boundaries. The front that separates a mass of cold air from a mass of warm, humid air becomes a region of extreme weather activity. The warmer air is quickly forced upward by the colder, denser air wedged beneath it. Lines of thunderstorms spanning hundreds of miles may be triggered by this lifting. As these squall lines sweep across the terrain, they bring with them a lot of rain, wind, and lightning. A rolling flurry of flashes can be produced by lightning that is almost constant along a squall line. These storm lines are visible from a distance as walls of darkness that are sometimes illuminated from within. They combine the force of structured storm systems with the visual drama of lightning to create some of nature's most striking displays. Forecasters keep a close eye on frontal boundaries since they are known to be hotspots for lightning and severe weather. Every day, lightning strikes the beaches due to sea breeze fronts. Predictable lightning patterns are produced in coastal areas by the daily cycle of heating and cooling. Because land warms more quickly than water during the day, cooler, moister air is drawn inland from the sea and rises over the land. Where the warmer land air meets the maritime air, this sea breeze forms a barrier. Thunderstorms that form in the afternoon and move inland are caused by the collision. Sea breezes from the Atlantic and Gulf coasts converge over the Florida Peninsula, which is a major factor in the state's frequent lightning. Other beaches throughout the world exhibit comparable trends. Because sea windstorms are predictable, locals can make plans to avoid them. During the warmer months, thunderstorms frequently occur in the late afternoon. In these areas, the daily rhythm of thunder and lightning becomes a frequent occurrence, punctuating summer days. Thunder science. The sound of thunder changes depending on the terrain and distance. The distance and obstruction between you and the lightning determine the kind of thunder. Thunder is a sharp, loud crack that occurs nearby because the sound wave hasn't had time to diminish and spread. Thunder turns into a rumbling with increasing distance. An overlapping sequence of noises is produced when sounds from several locations along the lightning channel arrive at somewhat different times. Thunder is also influenced by terrain. Echoes are produced, and the rumble is prolonged by hills and structures that reflect and disperse sound waves. Thunder may be more distinct and last less time in wide spaces like plains or over water. It can roll and resonate for many seconds in towns or mountains. The way sound travels is influenced by temperature and humidity, which can sometimes make thunder audible from a surprising distance or unexpectedly muffle it. No two thunderclaps are exactly the same since each one is shaped by a different combination of elements. After its first shockwave, thunder is subsonic. The air is heated by the lightning channel so quickly that it first produces a supersonic shockwave that travels faster than sound. The harsh crack from adjacent lightning is this shockwave. The shockwave, however, quickly transforms into a regular sound wave that travels at the standard speed of sound, which is roughly 760 miles per hour at sea level. Thunder is perceived differently at different distances due to this change from supersonic shock to subsonic sound wave. Those who are closer can hear the shock wave crack, but those who are farther away can only hear the subsonic rumble. To learn more about the energy of lightning and the atmospheric conditions that exist during storms, researchers have looked at the auditory characteristics of thunder. Thunder is a source of information about the lightning that produced it, not merely a byproduct. Lightning's infrasound may travel great distances. Thunder contains infrasound, or frequencies that are below the human hearing range. Far beyond the spectrum of audible thunder, these low-frequency waves can travel hundreds of miles. Researchers can identify lightning strikes that happened far beyond the horizon by using specialized instruments that can detect this infrasound. Lightning detection is one use for infrasound monitoring networks, which were first created to identify nuclear tests. The phenomenon shows that the impact of lightning is felt far more widely than is visible to the naked eye. Although we can only hear thunder within 10 miles or so, instruments can detect the subsonic roar that continues to reverberate outside. Every thunderstorm broadcasts its existence over large areas because of this hidden auditory signature, a signal that was silent and moving through the atmosphere. Thunder may be sensed by animals earlier than by people. It seems that many animals can detect impending storms before people do. Dogs can get nervous. Cattle look for cover. Additionally, birds alter their behavior. There is proof that animals can hear low-frequency sounds from distant thunder that people cannot. However, some of this may be because they can detect changes in humidity or barometric pressure. They can frequently hear at frequencies that are both below and above human thresholds. They might also be susceptible to thunderstorm-related electromagnetic alterations. For millions of years, animals were able to thrive in the wild by avoiding the perils of lightning and extreme weather conditions because of their sensory awareness. Before the invention of modern forecasting, our ancestors used animal behavior to anticipate the weather. These enduring awareness patterns serve as a reminder of the interdependencies between atmospheric conditions and living organisms. The rolling nature of thunder is caused by distance and reverberation. Thunder's distinctive rolling rumble results from the sound coming from several locations along the lightning channel at various intervals. Both horizontally and vertically, a lightning bolt can extend for several miles. You hear sound from the closest section first, then from parts that are getting farther away. Furthermore, sound waves create echoes that overlap with the original sounds when they reflect off of hills, buildings, clouds, and the ground. All of these noises combine to form the long-lasting roar that we know as thunder. Thunder may be shorter and more direct in wide, level spaces with few surfaces that reflect light. It can roll and reverberate throughout the area for up to 15 seconds in complicated terrain. Because of its intricate acoustics, thunder is not just loud, but also rich and layered, changing with each storm and place. Life and lightning. It's possible that lightning ignited the beginning of life. According to one intriguing theory, lightning may have contributed to the emergence of life on Earth. Lightning's energy may have fueled chemical reactions that produced amino acids and other organic chemicals in the early environment, which was abundant in methane, ammonia, and other simple molecules. This possibility was illustrated by the well-known Miller-Urey experiment in the 1950s, which used electrical sparks to create amino acids while mimicking early Earth conditions. Lightning is still a likely contributor to prebiotic chemistry, even though the precise conditions of the early Earth are still up for debate, and other energy sources, such as ultraviolet radiation and volcanic heat, also played a role. Innumerable lightning strikes could have created enormous amounts of organic molecules over millions of years, enhancing pools and oceans with the elements necessary for life. If this theory is right, then lightning was a creative force that helped create biology itself, in addition to being a strong phenomenon. Life-sustaining nitrogen is fixed by lightning. Although synthetic fertilizers play a major role in modern agriculture, natural sources of fixed nitrogen were essential before their development. The first of these sources is lightning. Most organisms cannot access the comparatively inert nitrogen in our atmosphere. The tight connections that hold nitrogen molecules together are broken by the heat of lightning, allowing the atoms to mix with oxygen. Rain causes these nitrogen oxides to break down, releasing nitrates onto the ground for plants to consume. Lightning is nevertheless important, especially in environments that are remote from ocean sources of biologically fixed nitrogen, even though it supplies less nitrogen than biological nitrogen fixation by bacteria. Lightning has been continuously transforming atmospheric nitrogen into forms that life can use throughout Earth's history, supporting plant growth and, consequently, all species that rely on plants. Through fires, lightning affects the composition of forests. For hundreds of millions of years, ecosystems have been changed by lightning-caused fires. Lightning strikes are rejuvenating forces in fire-adapted woodlands. They make room for certain plant species, remove undergrowth, and release nutrients that have been trapped in decaying wood. Cones of certain trees, such as lodgepole pine and jack pine, only open and release seeds when they come into contact with fire heat. Periodic burns are essential to the regeneration of these species. Forests would become dense, dark, and dominated by species that can withstand shade if lightning-caused fires didn't occur, diversity would be lost as the ecosystem changed. Fires started by lightning preserve a patchwork of aging stands, resulting in a diverse range of habitats. Native Americans noticed these trends and occasionally used controlled flames to imitate them. The complex and age-old link between fire, lightning, and forest composition serves as a warning that ecological health frequently depends on disturbance. Trees with lightning wounds tell tales of survival. A characteristic scar, a spiral or vertical strip where bark has been blasted away and wood is exposed or burnt, is frequently left behind by lightning strikes on trees. These scars are caused by the electrical current passing through the outer layers of the tree, which are rich in moisture. In certain instances, the tree endures and keeps growing, leaving a scar that serves as a permanent reminder of the attack. Foresters and ecologists can determine the frequency and patterns of lightning in a region by examining these scars. Trees that are decades or even centuries old and have numerous lightning scars are not unusual in old-growth woods. The fact that these survivors survived severe electrical discharges and are still alive is evidence of their tenacity. The scars serve as a reminder that lightning is not always lethal, and that nature has an amazing ability to recover from even the most severe injuries. During storms, several animals become electrosensitive. Although there isn't much concrete proof, there are hints that some animals may be electrically sensitive enough to sense storm-related changes in the atmosphere. For hunting, sharks and certain fish have well-documented electroreception systems. However, it is still unknown if terrestrial animals are able to detect the electrical fields of impending storms. Anecdotal evidence from wildlife observers, farmers, and pet owners points to behavioral shifts occurring hours before storms hit. The potential of direct electrical sensitivity is nevertheless intriguing, even though other indicators like barometric pressure or wind variations may account for a large portion of this. Investigating these possible capacities may uncover previously undiscovered sensory capacities and expand our knowledge of how living things interact with their electromagnetic surroundings. If such sensitivity is real, it is a feature of the natural world that science has yet to fully describe. Lightning readiness and safety. The majority of lightning deaths happen outside while people are having fun. There are definite trends in lightning casualty statistics. Most fatalities and injuries happen when people are trapped outside during a storm. A significant percentage of incidents are related to recreational activities, such as fishing, boating, golfing, hiking, camping, and trekking. These kinds of activities frequently occur in open spaces with limited cover. Recreational users could be less aware of weather patterns or reluctant to stop their activities when storms are coming. This emphasizes how crucial weather knowledge is. Check the weather forecast before you go outside. Have a strategy for where to seek refuge in the event of a storm. A lot of deaths can be avoided. Early warning indicators like distant thunder or darkening skies are frequently disregarded by victims. Risk is greatly decreased by taking a cautious approach and fleeing the area as soon as thunder appears. Being attentive and making wise choices both before and during storms are key components of lightning safety. The 3030 rule offers helpful direction. Experts on lightning safety advise following the 30-30 rule. Count the seconds before thunder is heard after you see lightning. You should take shelter right away if it is 30 seconds or fewer because the storm is within 6 miles. Since storms can send lightning up to 10 miles distant, a 6 mm range offers a margin of safety. Resuming outdoor activities after the storm has passed should be done at least half an hour after the final thunder. Since storms can emit lightning even as people move away, many injuries result from people leaving shelter too soon. The 3030 rule is easy to remember and works well. Tragedies can be avoided by teaching it to kids and practicing it yourself. It turns ambiguous danger into a specific, doable rule that everybody can abide by. During storms, no outside area is totally safe. Many people believe that if you take measures, you can be safe in some outdoor areas, such as open fields or under trees. As a matter of fact, no outside area is safe when lightning is nearby. Despite their allure as rain shelters, trees are very harmful. Standing beneath a tree increases your danger of a direct strike or a side flash, in which current jumps from the tree to you. Lightning frequently strikes tall, isolated objects. Since you become the tallest object, open fields are also dangerous. Water conducts electricity well, so stay away from it. Poles, rails, and fences made of metal should also be avoided. The only safe places are inside metal-roofed cars or large structures with wiring and plumbing that can safely carry electricity to the ground. Realizing that outdoor areas are always dangerous during storms motivates quick action to locate appropriate shelter. Crouching is not a solution, it is a last resort. The crouch position is occasionally advised as a last resort if you are out in the open with no shelter and lightning is about to strike. In order to minimize touch with the ground and make yourself as small as possible, you must crouch on the balls of your feet. According to the idea, this stance minimizes the region through which ground current can travel and lowers your height, making you a less likely target. This stance should never be viewed as a solution, though, as it provides very little protection. Avoiding situations when it is required is the best course of action. Before storms arrive, get appropriate shelter. Crouching is a last resort, and it's quite dangerous to rely on it. It should constantly be emphasized when teaching this approach that the real solution is to stay indoors during storms. Plumbing and windows are susceptible to lightning strikes. Some safety measures are required even indoors. Buildings can be struck by lightning through windows, plumbing, and electricity. Because lightning can pass via phone wires, corded phones should not be used during storms. Avoid windows since there is a chance of side flashes and glass breaking from nearby hits. Plumbing should not be handled. Water pipes can conduct electricity, so avoid using faucets, showering, or doing the dishes. Despite the fact that surge protectors offer some protection, electrical gadgets should ideally be unplugged. Although most contemporary structures are reasonably safe, especially when equipped with adequate lightning protection systems, taking these safety measures gives an additional degree of security. Prudence, not paranoia, is the goal of these rules. Although lightning rarely enters buildings, when it does, there can be serious repercussions. During storms, simple behavioral adjustments reduce already minimal dangers. And finally, lightning research's future. Lightning prediction is getting better thanks to advanced sensors. Meteorology is still developing. Additionally, modern technology is increasing lightning prediction. Sensor networks are able to identify not only lightning strikes, but also the electrical fields that form before strikes happen. Sometimes these sensors may send out alerts just minutes before lightning strikes, giving people time to find cover. Specialized instruments on satellites provide worldwide coverage of lightning strikes, even those over oceans and distant regions. By analyzing trends in atmospheric data, machine learning algorithms are able to more accurately anticipate conditions that are likely to create lightning. The tendency is evident, even though precise prediction is still challenging. Forecasts become more accurate, warnings more timely, and the public better informed as sensor networks grow and algorithms advance. In addition to saving lives, this advancement helps society better anticipate and address lightning risks. Missions in space examine lightning from above. Seeing lightning from above offers viewpoints that are not attainable from the ground. Lightning mapper-equipped satellites are able to simultaneously detect and locate strikes over whole continents. By monitoring storms from above, they are able to record the entire spectrum of lightning activity, including intra-cloud discharges that are not visible from the ground. The global distribution of lightning has been made visible by these missions, revealing patterns and hotspots that aid scientists in their understanding of atmospheric dynamics. Transient light occurrences such as elves, jets, and sprites are also seen by space-based studies. Phenomena that are hard to see from the ground and that take place above storm clouds. These missions' data support climate study, enhance forecasts, and input into weather models. A planetary viewpoint of lightning seen from orbit shows how electrical activity fits into the larger dynamics of Earth's atmosphere. Lightning patterns may shift as a result of climate change. Scientists are researching how lightning might evolve as the world's climate warms. Increased storm energy could result from warmer temperatures, which could cause thunderstorms to be more intense and lightning to occur more frequently. According to some forecasts, lightning will increase by 10 to 12% for every degree Celsius of global warming. The formation of thunderstorms is influenced by variations in atmospheric circulation, precipitation patterns, and moisture availability. Storm location and timing changes may change the distribution of lightning, influencing ecosystems that are acclimated to particular fire regimes and infrastructure in areas where lightning is not common. Climate change has the potential to alter lightning patterns, although research is still in progress and forecasts are subject to uncertainty. Society can better prepare for a future with potentially different lightning threats than those of the past by keeping an eye on these changes. One of nature's greatest mysteries is still lightning. Scientists are still trying to find answers to the mysteries surrounding lightning, even after centuries of research. Ball lightning's precise processes are still unknown. The specifics of charge separation in clouds are still being worked out. It is not quite clear what triggers cause a step leader to start dropping. Even the overall energy content and distribution of a lightning bolt are still being measured and discussed. Every storm is different, every bolt is different, and lightning defies easy classification due to the intricacy of meteorological variables. This timeless enigma contributes to the allure of lightning. It serves as a reminder that science is a continuous process of discovery rather than a definitive list of facts, that even known events can surprise us, and that nature still has mysteries. Lightning as inspiration. Innumerable pieces of art have been influenced by lightning. Throughout history, artists have endeavored to depict the beauty and power of lightning. Painters use lightning to illuminate stunning landscapes or seascapes during storms. Photographers use technical expertise, perseverance, and good fortune to capture the ideal lightning photo. Lightning is a metaphor used by authors to symbolize unrestrained energy, supernatural intervention, or startling understanding. Musicians use crescendos and percussion to conjure images of thunder and lightning. The difficulty of portraying something so ephemeral and potent has captivated artists from all backgrounds and times. In addition to being beautiful objects, these pieces are reflections on the might of nature, the insignificance of humans, and the profound beauty inherent in forces outside of our control. In art, lightning serves as a reminder that the natural world is a never-ending source of inspiration, that beauty and fear may coexist, and that people have long tried to document and comprehend the occurrences that influence their surroundings. Lightning and storms elicit strong emotional reactions. Watching a lightning storm has a profoundly affecting quality. For some, it is an exhilarating demonstration of the force of nature that inspires wonder and excitement. Others sense worry or anxiety, particularly if they have had close calls or harm in the past. Youngsters frequently respond to windows with awe, pushing their faces against them and asking inquiries. Sensing the commotion, pets may hide or shudder. Individual experiences and temperaments are reflected in these diverse and natural emotional reactions. Following a storm, the air can feel rejuvenated and clean. They serve as a reminder of forces beyond our control and sometimes seem menacing. They can be humble, captivating, and lovely. The diverse character of lightning is reflected in the emotional richness of our responses to it. In many mythologies, lightning represents transition. It is both dangerous and alluring, destructive and necessary to the natural world. Beyond its connotations of might and divinity, lightning frequently symbolizes abrupt change or epiphany. Lightning symbolizes turning points in mythology and narrative, altering characters or objects as it strikes them. Lightning is occasionally invoked by initiating rites as a representation of the experience's transformational potential. A lightning bolt of understanding is a typical metaphor used in psychology to describe startling breakthroughs known as aha moments. The essence of lightning is reflected in its metaphorical meaning: abrupt, short-lived, and able to leave lasting effects. All cultures may relate to the idea that lightning changes anything it comes into contact with, either literally through fire and destruction or figuratively through enlightenment. It touches on how people deal with change, how change frequently occurs powerfully, abruptly, and without warning. Our obsession with lightning is reflected in popular culture. Lightning imagery is ubiquitous in contemporary media. Characters that can control electricity are common in superhero comics and movies. Their abilities were pictured as lightning bolts. Applications of technology are explored in science fiction, ranging from electrical discharge-inspired propulsion systems to energy weapons. Lightning is used in horror to create tension and build the mood by vividly lighting situations. Lightning is even used in advertising to communicate power, speed, and energy. Lightning is used in video games as a gameplay element and visual spectacle. This widespread use shows that lightning is still a major cultural emblem that has both emotional and visual resonance. Understanding hasn't made us any less fascinated. If anything, the phenomenon is made more impressive, not less, by understanding the science. Ancient awe and modern knowledge are connected by lightning, retaining its strength in both reality and imagination. While lightning occurs throughout the year, in many places it peaks in the summer. Summer is lightning season in temperate regions. Strong solar heating, high humidity, and warm temperatures all contribute to the development of thunderstorms. Storms frequently develop in the afternoon and evening when the sun heats the ground during the day. Lightning activity tends to peak at the height of summer. People modify their routines, organizing outside activities for mornings when storms are less likely, or following forecasts attentively. Like long days and warm evenings, summer lightning storms are an expected component of the seasonal cycle. The trend is different in tropical areas, where lightning is more closely associated with the wet and dry seasons than with temperature. Nevertheless, Lightning becomes a distinguishing feature of that season, influencing how people live and make plans, wherever seasons produce times of increased thunderstorm activity. Though uncommon, winter lightning is powerful. Winter thunderstorms are uncommon in colder regions. The atmospheric instability required for storms is rare because cold air does not retain much moisture. Winter lightning does, however, infrequently happen and is frequently linked to heavy winter storms or lake effect snowbands. It can be shocking when it happens, a summertime phenomenon that shows up in the middle of snow. An eerie and unforgettable experience is produced by thunder, snow, and lightning during a snowstorm. Thunder is muffled by the snow, which makes it shorter and quieter than in the summer. Bright lightning and falling snow provide a startling visual contrast. In many locations, winter lightning is so uncommon that individuals may not see it for years, making each sighting unforgettable. It reminds us that lightning is essentially about atmospheric processes that, under the correct circumstances, can happen all year long. Severe weather and lightning are common in the spring. The most dramatic collisions between warm and cold air masses occur during the transitional season of spring. Some of the most extreme weather of the year, such as supercell thunderstorms, tornadoes, massive hail, and a lot of lightning, is produced by this collision. Massive spring storm systems that span several states and linger for hours or even days are possible. These storms produce powerful, frequent, and occasionally almost constant lightning. In the spring, storm chasers appear, scouring the Midwest and Great Plains for severe storms. In many areas, springtime means being alert, keeping an eye on forecasts, and being ready for severe weather. In addition to being stunning, spring storm lightning is an indication of the storm's strength. It serves as a warning about the energy in the atmosphere, energy that can show itself as any kind of severe weather, not only lightning. As the seasons change, autumn storms can be fierce. Another transitional phase occurs in the fall, albeit it is usually milder than in the spring. Even if the summer heat is starting to subside, strong thunderstorms can still occur when warm air masses occasionally move northward and collide with cooler fall air. During hurricane season, tropical systems that move inland in some areas bring with them embedded thunderstorms with a lot of lightning and heavy rain. Compared to summer storms, autumn storms frequently have a distinct personality, occasionally more extensive and persistent as opposed to isolated and transient. Due to the shorter days, storms that form in the late afternoon swiftly turn into nighttime, lighting the darker skies with spectacular lightning displays. The storm season is coming to an end with fall lightning, a final flourish before the normally calmer weather of winter. The storms seem like a natural part of nature's year-end transition. Lightning strikes tropical places all year round. Lightning is a common occurrence close to the equator, where temperatures are consistently warm and there is an abundance of moisture. Converging winds and sun heating can cause tropical thunderstorms to form on any given day. With storms frequently forming in the afternoon and evening, the daily cycle of heating and cooling produces regular patterns. Thunder and lightning are common sounds found in rainforests and are a part of the natural acoustic environment. In tropical areas, lightning is a year-round phenomenon that influences nutrient cycles, fire regimes, and biological patterns. For residents of these regions, lightning is a constant occurrence rather than a seasonal one, and they need to be mindful of it at all times. Cultural perceptions of lightning are shaped by this constancy, which makes it less of an occurrence and more of a common occurrence under tropical skies. Lightning poetry. Poetry is written across the sky by lightning. The poetic quality of lightning is intrinsic. Its abrupt light, its branching shapes, its fleeting presence. Lightning has long been utilized as imagery and metaphor by authors and poets. It stands for power, suddenness, clarity, and revelation. Natural analogies are created when lightning branches mimic trees, rivers, or veins. Its light against the black represents hope in despair or knowledge piercing ignorance. Thunder and lightning together serve as a metaphor for forces that invariably coexist or for cause and effect. What science cannot describe, poetry can. Lightning's aesthetic and emotional impact, while physics explains how it occurs. Poetry captures the experience of seeing it. Both viewpoints are useful, and when combined, they help us understand this phenomenon more thoroughly. Every lightning bolt is different and cannot be duplicated. Never are two lightning bolts precisely the same. Each travels a route dictated by the particular atmospheric circumstances at the time. The way ions, dust, and moisture are distributed. There are variations in the duration, strength, number of return strokes, and branching pattern. Because of its uniqueness, each lightning bolt is a one-of-a-kind occurrence that only occurs once and never again in that same form. This transience enhances the beauty of lightning. There is no way to reproduce it, just observed and recalled. Photographs preserve special moments by capturing individual shots. However, even pictures are only depictions. It is impossible to match the real experience of viewing lightning with its intensity, suddenness, and subsequent thunder. Every storm presents a sequence of singular occurrences that will never be replicated. Presence of the day. Time is marked in memory by lightning. A lot of people may remember particular lightning storms from previous years or decades. Maybe a storm as children that scared or amazed them. A strike that struck close enough to feel its power. A stunning spectacle seen while traveling. Vibrant sensory aspects, such as the brightness, the sudden boom of thunder, the smell of ozone, and the sound of rain drumming, are frequently included in these memories. Because lightning stimulates many senses at once and frequently arouses intense emotions, it produces powerful memories. In our personal narratives, these memories serve as markers, moments that contrast with the routine of everyday life. Remembering them allows us to re-establish a connection with our younger selves, reliving the awe or horror we once felt. Thus, particular bolts and storms are woven into the fabric of each person's past, making lightning a part of our story. For those who are not afraid, watching lightning can be a form of meditation. It can be quite soothing to observe a distant lightning storm. A meditative state is promoted by the rhythm created by the storm's slow progress across the landscape, the deep rumble of thunder, and the repetitive flashing. The mind can relax into silent observation while sitting on a porch or gazing out a window toward the horizon as lightning pulses. The display's hypnotic quality comes from the way light repeatedly reappears after emerging from darkness. Personal worries are put into perspective by the enormity of the occurrence, which involves enormous forces operating over miles of sky. When you witness the storm, you temporarily lose yourself in the present and become a part of something greater than yourself. The meditative nature of storms contributes to their perceived force and tranquility. We are connected to one another across time via lightning. Every living thing has witnessed lightning. One of the genuinely universal human experiences that transcends all cultures, eras, and places is this one. Though they had a different interpretation, the ancient thinkers observed the same occurrence that we do today. This sensation is shared by enlightened scientists, Renaissance artists, medieval peasants, and contemporary kids. You become a part of an uninterrupted line of observers that dates back to the dawn of human consciousness when you watch lightning. It could mean different things to us. Where we see physics, our ancestors saw gods, but the experience itself, the flash, the thunder, the awe, brings us together. One of the things that all of us humans have in common is lightning. It serves as a reminder that, in spite of our differences, we have essential experiences in common with everyone who has been before us and everyone who will. We are able to access the ancient atmosphere through lightning. The same laws that controlled lightning millions of years ago still apply to every lightning bolt that flashes now. Dinosaurs saw lightning storms long before humans did. Mammals in the past sought refuge from them. They were feared and revered by our distant ancestors. The basic physics of electrical discharge has not altered across geological time, despite changes in the temperature and makeup of the environment. When you observe lightning, you are taking in a phenomenon that has existed on Earth since the planet's formation of a significant atmosphere. It serves as a reminder that we are a part of a story that extends far beyond human history and a link to deep time. Lightning existed before humans and will persist for a very long time, a constant characteristic of a dynamic environment. Lightning serves as a reminder of the beauty and might of nature. It is simple to forget that we live on a dynamic planet in our contemporary world of regulated settings and technological isolation, controlled by strong natural forces. One of the most obvious reminders is lightning. Even with all of our advancements, we are unable to completely control or prevent lightning. All we can do is get ready, keep safe, and show respect. It's good to be humble. It helps us remember that we are a part of nature, not something distinct from it. Lightning also demonstrates that beauty and power are not mutually exclusive. The same phenomenon that has the power to harm may also inspire, create, and light up. The dichotomy of lightning, destructive yet necessary, terrible yet beautiful, reflects the complexity of nature. It teaches us to respect danger and value beauty at the same time, and to cling on to seemingly incompatible beliefs. The potential energy of lightning is present in every storm. Be aware that millions of collisions are taking place within storm clouds as they are gathering. In the updrafts, water and ice are dancing, swapping charges every time they come into contact. Electrical fields are accumulating, becoming more powerful by the minute. Like a battery that is gradually being charged, the storm holds energy that will finally be released as lightning. In every thunderstorm, this process is ongoing, silent, and invisible. The storm has been building toward that releasing point by the time the first bolt flashes. Our perception of storms is altered when we realize this covert preparation. They are dynamic systems that are always changing rather than static items. Energy builds up and flows until it is released in dazzling bursts. Every storm is a separate electrical environment. Hidden intricacies have been exposed by lightning photography. Prior to high-speed photos, lightning's structure was mostly undetectable. The bolt's general outline is all that is visible to the human eye. However, lightning may be captured in stunning clarity by cameras with quick shutter speeds and sensitive film or sensors. The branching structure, numerous return strokes, and occasionally even the leader's stepwise evolution are all visible in these pictures. Both scientists and amateurs may now study what was previously invisible thanks to slow-motion video, which depicts activities that take place in milliseconds. Photography has made it possible for anyone with a camera to record and study these intense eruptions, democratizing lightning observation. Every picture is both fact and art. They are both visually stunning and helpful for comprehension. Lightning photography, which combines nature and technology, has provided new insights into this age-old phenomenon. Traces of lightning strikes can be seen in the ground. Lightning causes more subtle wounds than the visible ones on buildings and trees. One example is the glassy tubes called fulgurites that form in sand. However, rock and soil also develop magnetic anomalies as a result of lightning. When surveying sites, geologists and archaeologists occasionally come across these magnetic traces because the strong current can magnetize iron-bearing minerals. Additionally, lightning strikes have the ability to chemically change soil, producing enhanced nitrogen molecules in specific locations. When lightning strikes a forest, the area may exhibit atypical plant growth in the following seasons, either boosted by nutrients or inhibited by soil structural damage. These traces act as transient documentation of lightning's passage. However, they gradually disappear. In these subtle ways, lightning is remembered by the Earth itself, at least momentarily. For generations, people have used thunder to gauge the distance between storms. People used to count the distance between lightning and thunder to estimate storm distance long before meteorological equipment was invented. This traditional knowledge that has been handed down through the ages is based on sound physics. Sound moves at a quantifiable pace, whereas light is essentially instantaneous over the distances involved. The gap is the interval between hearing and seeing. Farmers make decisions on whether to seek shelter or keep working based on this information. It was used by sailors to determine if a storm was coming or going away. Parents taught it to their children as a useful skill and a means of calming anxiety, making the storm something that could be quantified and comprehended. This straightforward method is among the first examples of how science was applied to daily life by humans. Lightning has been known to cause migraines and other sensitivities even before the underlying science was completely understood. Lightning storms are said to cause headaches, especially migraines, according to some people. Although the exact mechanisms are unknown, a number of elements could be involved. Storm-related variations in barometric pressure are known to cause migraines. Sensitive people may be impacted by lightning's electromagnetic fields. Lightning-induced ozone generation may contribute to changes in air ionization. Tension and stress pathways may be involved in the tension and anxiety that some people experience during storms. Although not everyone is affected, storms become dependable causes of misery for those who are. By being aware of possible triggers, people can take precautions like taking medicine prior to a storm or limiting their exposure to stresses associated with storms. Medical professionals and meteorologists are still interested in the intricate relationship between atmospheric phenomena and human physiology. Ozone is produced in the upper atmosphere by lightning. Ozone formation is one of the atmospheric impacts of lightning. Ozone is created when oxygen molecules split apart and reunite in the three-atom configuration due to the strong UV light and heat from lightning. The high atmosphere is where most of this ozone generation takes place. The cumulative effect of millions of lightning strikes per day contributes to atmospheric chemistry, even though the amounts created by individual strikes are minimal. The sun's damaging UV rays are absorbed by the helpful ozone in the upper atmosphere. As a result, lightning has a minor yet beneficial impact on the ozone layer. This is distinct from the contaminant known as ground-level ozone. Lightning is similar to ozone in that it is both beneficial above and dangerous below. It is yet another illustration of the intricate and perhaps surprising ways in which this phenomenon affects the environment. Ozone contributes to the after-lightning odor. A characteristic, sharp, clean odor frequently lingers in the air after a nearby lightning strike. The ozone produced by the electrical discharge is partly responsible for this smell. Ozone has a distinct smell that is frequently compared to chlorine or metal. One reason why people think of storms as clean and fresh is because of their scent. The smell of ozone adds to the feeling that the air has been revitalized following a storm. But there are other aspects as well. Rain causes substances to be released from the soil, a process known as petrichor, which has a nice earthy scent of its own. The amount of negative ions created close to lightning and waterfalls may also have an impact on how we perceive the quality of the air. A storm's multisensory experience, sight, sound, and smell, forms strong memories and associations that last a lifetime. TV and radio can be disrupted by lightning. Lightning's electromagnetic pulse produces radio frequency interference over a wide range of frequencies. Lightning, sometimes from storms hundreds of miles distant, can be detected by AM radio receivers as static or crackling noises. There may be temporary interruptions to television transmissions. During storms, ham radio operators learn to identify lightning interference and steer clear of specific frequencies. Prior to the widespread use of satellite and cable, television images would flutter and warp when lightning struck close. This interference is a tool as well as an annoyance. In order to comprehend electrical processes in the atmosphere, radio astronomers investigate radio waves produced by lightning. Radio receivers tuned to lightning frequencies are used by weather agencies as part of their detection networks. The location, strength, and kind of lightning discharges are all revealed by what appears to be random noise. When properly understood, even interference might be considered data. The evolution of electrical engineering has been influenced by lightning. The field of electrical engineering was directly impacted by the study of lightning. Gaining an understanding of voltage, current, resistance, and impedance was necessary to comprehend lightning. Surge protectors, grounding systems, and shielding techniques had to be developed in order to defend against lightning. All electrical systems made use of these lightning-related solutions. Lightning protection technology is the ancestor of surge prevention in computers, building grounding, and power line insulation. Since systems that can withstand lightning will function well in everyday situations, electrical engineers study lightning as an extreme scenario. Lightning pushes the limits of what electrical systems can tolerate and can be both an inspiration and a worst-case scenario. Making sure that contemporary grid infrastructure can withstand lightning strikes, which are unavoidable over wide geographic areas, is still a difficult task. Education can help children who are afraid of lightning. A lot of kids are afraid of thunderstorms because of the dazzling lightning and loud thunder. This fear is a normal, evolutionary reaction to a real threat. But too much worry can be upsetting. Parents and teachers have discovered that comprehension is beneficial. Fear can be turned into curiosity by describing the causes of lightning and thunder, stressing that staying inside keeps you safe, and having kids count the seconds between lightning and thunder. Children can better understand storms as natural occurrences rather than dangers by reading books and participating in weather education programs. Children get empowerment and a sense of control when safety regulations are taught to them. Some kids find it exciting rather than frightening to observe storms from a safe place with a responsible adult. The shift from dread to interest teaches us that knowledge eases anxiety and that nature is less dangerous when we comprehend it. For millennia, scientists have been fascinated by lightning. Numerous scientists have pursued careers in electrical engineering, atmospheric physics, and meteorology as a result of studying lightning. Many academics think back to their early years, when they watched storms from windows or porches, curious and trying to make sense of what they were experiencing. Lightning is reachable. To view it, you don't need a telescope or microscope. For young people who are interested in science, its drama captivates their attention and imagination. Lightning offers the ideal point of entry, evident, potent and not quite comprehended. Questions inspired by thunderstorm observations have spawned research careers. This loop keeps going. There are those in every generation who are fascinated by lightning and dedicate their lives to solving its unsolved secrets. This sensation of wonder is necessary for science, and lightning consistently delivers it. Beyond meteorology, lightning research has real-world applications. Numerous fields have improved as a result of our growing understanding of lightning. A deeper comprehension of the relationship between lightning and aircraft has improved aviation safety. Research-based lightning protection requirements are incorporated into building codes. Lightning-induced surges are taken into account in power system design. Systems for communication are designed to withstand electromagnetic interference. Composites that are resistant to lightning strikes are created via materials science and used in wind turbines and airplanes. Medical knowledge of lightning injuries helps in trauma treatment, since lightning can disrupt rocket launches and necessitate precise forecasts. Even space exploration benefits. Lightning research's wide range of applications shows how researching a natural event can have benefits in a variety of fields. Curiosity about lightning has led to pure research that has produced useful knowledge that safeguards infrastructure and lives. The energy of lightning slowly diffuses into the atmosphere. Following the hit that has taken place and the channel that has cooled, the lightning energy does not disappear, but rather disperses, following the bright flash and rumbling thunder. The air around them gets a little warmer as the heat radiates outward. Ozone disperses and drifts. Rain causes the nitrogen compounds to break down and fall to the ground. At the speed of light, the electromagnetic pulse spreads outward, becoming weaker over distance until it completely disappears. For a split second, what was concentrated in a pencil-thin channel becomes diffuse and dispersed throughout cubic miles of atmosphere. Gentle dissipation replaces the original discharge's violence. Lightning's energy is thus altered but not destroyed as it returns to the environment. Energy is only altered, it is never gone. And the energy of lightning, which was previously so powerful and focused, returns to the atmosphere. All storms pass in time. Every thunderstorm ultimately runs out of energy, regardless of how strong or long it lasts. As the amount of accessible moisture decreases, the updrafts become weaker. Through progressive leaking and lightning, the electrical charge diminishes. The atmosphere is stabilized, and the air is cooled by the rain. The clouds thin and break apart as the storm dissipates. The stars are back, or the sky is blue. What was tumultuous and dark becomes clear and serene. The rhythm of nature includes this cycle of intensity and quiet, build-up and release. It is impossible for storms to persist forever. They are transient atmospheric disruptions. Though limited, they are strong while they last. At the height of a storm, it is comforting to know that it will pass. The lightning will stop, the thunder will subside, and the silence will return. With storms rising and falling like waves, and each one being transient against the continuous atmosphere, this pattern keeps repeating indefinitely. The world feels rejuvenated after the storm. After a thunderstorm, the air has a certain quality. The temperature has occasionally dropped considerably. Rain has wrung out the oppressive humidity that preceded the storm. It feels like the air has been cleaned. The plants are renewed. Their leaves were spotless and gleaming with drops. The clearing sky is reflected in puddles. Singing again, birds may be heard clearly in the clean air. Tension seems to be released as the globe exhales. There are psychological and physical aspects to this post-storm regeneration. Rain, lightning, and downdrafts have actually changed the atmosphere by ionizing it, cooling it, and cleaning it. However, we also feel rejuvenated after seeing something strong and surviving the storm without incident. Our enjoyment of both is enhanced by the contrast between the storm's severity and the ensuing calm. We are reminded of the unending cycles of nature by lightning. Each thunderstorm is a component of a larger cycle. Lakes, soils, and oceans all lose water. Completes the cycle by ascending into the atmosphere, condensing into clouds, and then falling as rain. This cycle is powered by solar energy, which warms the surface and produces the instability that causes storms. One manifestation of this enormous flow of water and energy is lightning. It is intricately woven with nature rather than existing outside of it. Lightning-fixed nitrogen feeds plants, which in turn feed dead animals that re-enter the soil to produce new plants. Forests are cleared by lightning-caused fires, allowing for regeneration. Every facet of lightning is linked to more extensive cycles: life, death, rebirth, water, energy, and nourishment. A deeper appreciation for lightning results from knowing these links, recognizing it as a thread woven into the complex web of Earth's systems rather than as a singular occurrence. Now, when the thunder subsides into quiet, rest. And so our investigation into lightning comes to an end, dear listener. From the center of storm clouds to the ruins of old trees, we have been there. We have examined the beauty and power of lightning, its risks and advantages, and its function in both nature and human culture. From the fact that lightning pathways are hotter than the surface of the sun, to the silent release of energy into the atmosphere. We have looked at the science behind it and the unsolved riddle. Both familiar and able to evoke wonder, lightning is both understood and still startling. Imagine the peace after a storm as you get comfortable. The final thunderclap disappeared into the distance. Instead of stopping, the flashes are becoming less frequent, the clouds dissolving, exposing the moonlight or stars. Water drips steadily from the leaves. A window is open, letting in cool, fresh air. Following nature's demonstration of power, the world is at peace. Now, allow this calmness to descend upon you. Your body is calming down like the air after a storm. Your breathing is slowing, and your thoughts are becoming quiet. Find your own balance. As the storm discharges its energy, let go of the day's stresses. Experience a sense of calmness, grounding, and stillness. A spectacular and tremendous bolt of lightning has occurred. It is now fading. The sound of thunder fades into quiet, and you fall quietly and peacefully into the profound rest of sleep in that darkness, in that silence, in that beautiful calm after the storm. Good night.